How many of you have ever gone to the recording?
Like the old ones?
No, this no.
I did it from here.
Two of you, three. Sunny,
Today.
how relevant is the recording? Do you need the recording?
Yes.
Yes, just because last time I used that one, that's why I say yes.
The video is like that.
Whatever we write,
Yeah.
there is something important in that thing. That's why.
Okay. So two of you, how many care for the video?
I think all of us.
So that's significant. Okay. So I can take the effort. Okay.
And with past experience, that one is very
Yeah,
important.
that one before the exam, that video really helps.
Okay. So I'll keep trying to record. How did the homework one go?
Okay.
Be frank. Could you finish it?
Yes.
Only one?
The only part that was kind of like iffy was when you said investigate the case when h bar equals 0.
Oh.
How much investigation that entailed, apart from just saying this is the standard case when the components commute.
Good question. When it's a vague question like that, treat it like a quiz. You can explore it as much as you want, but usually little bit. Like what I meant there was what happens when h bar is equal to 0 and what is the expression you get. Is it consistent? If you're familiar with some quantum mechanics, then is it familiar with the limiting conditions? Yeah, that's what I meant. But yeah, that is all. Nothing more than that. And Rocky and Deepak, how was the homework? I asked you guys because you got new in Sanya. It's going well. Like, feel free to ask me after class. How much of the homework have you guys finished, if I can ask? I'm putting you guys on the spot.
Question number 6, I think my result is
So it is due at 4:30, so even now you have time and
6 is little lengthy, that's why maybe.
okay, it's lengthy. So the
Yeah,
next one is
6 was definitely the longest problem.
Yeah.
okay. Next one is lengthier. Next homework.
That's why I speed like I consider I as one first part, J the second part, and then solve 2, and then 8 is the last.
How about this? You can take a little bit extra time if you want to. Let's say 1 day more. You can make it tomorrow, but try to finish it off. Don't collect them. It won't help the course, right? But since it's the first week, so feel free to take some extra time. Contact me if you have difficulties. Usually, asking either your colleagues or me can significantly speed in the process. Usually it's notations issues. Okay. So shall I keep proceeding?
Yeah, sure.
Yeah. Okay, so we have homework 1 is done. So homework 2 I posted early in the morning today. We have Monday holiday, right? Is that correct? So Monday is, what's the date Monday? September 1?
Yeah.
It's labor. Okay, so homework 2, I cannot make it due on September 1. So it's due September 5th. So it's Friday. So it's about 10, or 11 days there. But then the next homework, I am tentatively making it due on Monday. It's not posted yet, so be aware of that and be responsible with dealing with the homework. Okay. We worked on some simple vector identities using index notation. Usually, index notation is also useful when there is a gradient operator showing up. So we want to introduce the gradient operator and start using that in conjunction with the ordinary cross product or distribution, if you want, that is happening, and that will usually expand this further out. Instead of the distribution going 2 times, it will go 4 times. So we'll see that here. So let's look at gradient operator. In very simple terms, it is a derivative in higher dimensions in space. The space is 3-dimensional. Unlike time, we have only one variable defining time. Space is 3. So when you think of a derivative, it is directionally dependent. It can be in either one of the directions. So we want to look at what gradient operation is. This is represented in this form. And in rectangular coordinates, it is a coordinate dependent representation, at least after the equality. When I write only the left hand side, that doesn't depend on any basis. But when I write the right hand side, that's a basis dependent quantity. So in rectangular coordinates, you will say this is I hat by dx plus j hat by plus k hat d by dz. I specifically say right hand side is in rectangular coordinate. It's a rectangular basis maybe. So it's a basis dependent quantity. Left hand side is, you want to think of this as a basis independent. So it is just our handicap that we often want to think of a gradient operation in some coordinates and the right hand side. So are there other bases? Yes, you can use at least the 3 most convenient or most easiest basis is the rectangular coordinates, spherical coordinates, and third is cylindrical coordinates. In fact, cylindrical itself gets quite hard in most of the situations. So it is only the planar and spherical cases which really helps you find complete solutions. So in most cases, I shouldn't say that's the only basis. In spherical coordinates, what is this equal to in spherical coordinates?
See, partial with respect to r, 1 over r partial. Is that?
So it has a dimension of 1 over length. So you already captured the 1 over length, so no 1 over r, right? And r hat, right? Plus theta hat times. So 1 over r.
Yeah.
So again, dimensionally, and phi hat is 1 over r sine theta. Okay. Fine, right. So that's in spherical coordinates. Again, and cylindrical, just for pointing out that the left hand side is the same object, but it's being written in different bases. So left hand side is basis independent, right? It's the same idea. And in cylindrical coordinates, this will be d by d rho. That's the 3 coordinates we will be mostly using as example. What are the other bases that sometimes help, at least in some certain geometries? Like these are the 3 most popular ones. Any other ones that you can think of?
Oh, like position and momentum basis.
It has to be three-dimensional space. So this is a basis for three-dimensional space itself. That becomes six-dimensional. Position is three, momentum is. So you can use a basis for momentum, a basis.
That's
for
what I was
position.
saying, not them together individually, position basis.
Yeah, in the position, what are the coordinates you can think of? Like spherical coordinates is convenient, cylindrical coordinates, or spherical polar coordinates, cylindrical polar coordinates, and then we have rectangular coordinates. What others? Is that the only three? And by that, of course, we can have many, but it turns out that you should have some advantage. At least you should be able to solve one problem using that coordinate system. Only then it works. And there is a list prepared by Morse and Feshbach back in 1930s. That's your textbook also. At least there is a reference which I suggest. So he lists 11 coordinate systems which can really separate, let's call electromagnetic problems. Or maybe I should say, first let's talk about scalar problems. It can be separated using 11 coordinate systems, and I'll try to at least point them out here. And only out of that, only 5 or 6 are very useful in electromagnetism. Remember, electromagnetism is quite involved in the sense it involves two fields, electric field and magnetic field. So to separate both of them becomes a challenge. So how do you see this? Rectangular coordinate systems are, I'm only showing the 2 dimensions part of this. So this is 2 lines. This is how you would do this. Is that clear what I'm saying? X and Y, right? That's your coordinate system. If you're doing spherical coordinates, you have spheres. So that's spheres. Right. That's the radius r, and the angle theta is this. These are cones. So that's your angle theta. Is that clear what I mean? So it's an intersection of spheres and cones, and phi is half plane. So it is sphere, cone, and half plane. So here there are 3 planes. So it is plane, plane, and a plane, right? All 3. Is that clear what I mean by that? Like if you think of cones of various opening angles, and each of this box that you consider, that's the infinitely tiny volume we are talking about. Here the infinitely tiny volume is rectangular. It's like a rectangle with very tiny limits, distances going very small. And here, this is that piece which you take out in the phi direction too. Cylinder, it's against cylinders this time. This is not sphere, this is cylinder. And half line, right? That's your phi, that's your rho, and this is a plane, a full plane. That's the z. Right? So you slice a cylinder with z. What are the others that you can have? Elliptic quantities, right? And then one is an ellipse, so this is, you rotate this out, and now you can have hyperboloid, so you can have spheroidal coordinates. And next one, you can have parabolic coordinates. And once you go to spheroidal and parabolic and elliptic coordinates, based on about which direction you rotate, there are more than one possibilities. And the third is elliptic coordinates. So your quizzes list all the 11 possible coordinates, or it's not that it's the only possibility. In 11 of these coordinates that I'm mentioning, the the Maxwell's equations separate out, or let's call it the wave equation. Maxwell's equation is going too far. The wave equation, which is what describes light, a plane wave, scalar wave equation, that separates and leads to nice solutions. So in how many coordinates does the scalar wave equation separate? We also need to talk about what a wave equation is. Probably the distinction might not be very clear. Wave equation, heat equation, and the Poisson equation that you see in electrostatics. Okay, but here my point was just the gradient operator. How do you visualize a gradient operation? What is the how do you intuitively see a gradient operator? So let's think of a particular example. Let's say I have a function. So, example. So let's have a function r which is dependent on x, y, and z. That's equal to x squared plus y squared plus z squared and the square root of it. If I were to plot this as a function of x, y, and z, what will I get? How will it look like? Sphere, right? So that's a sphere. So this is a sphere. And now I'll stop writing x, y, z just to avoid the clutter there. And now we want to visualize what is gradient of this function of. So since this is the first time we are trying to do an example, let's explicitly do this in rectangular coordinates. Remember, it doesn't need rectangular coordinates. Left hand side, if I were to just say r, that is also sufficient because that's in spherical coordinates. That's what sphere means. R is equal to constant. Like that's the equation of a sphere. In spherical coordinate, it just says that the radius r is equal to constant. If you write in rectangular coordinates, that's artificial in the sense it's not the most convenient basis for describing a sphere. Then you get this x squared plus y squared plus z squared. But our derivatives operations might be more convenient here at this point. So let's try that first. So this will be equal to I hat dy dx plus j hat dy dy. Just this is the long way of doing it. Let's do that. And acting on whole thing acts on x squared plus y squared plus this. That's equal to I hat dy dx of this, but I know how to operate that. It's 1 by 2. So I start with 1 by 2, the power of x squared plus y squared. When I take the derivative, it becomes minus 1, goes to the denominator. It's x squared plus y squared plus z squared. Then take the derivative of the argument, that's 2 times x. And do the same thing again. J hat 1 by 2, 2 times y over x squared two cancels out clearly. So you immediately see that the denominator is nothing but the function I started its with, so it is r, and the numerator is I hat x plus j hat y plus k hat z divided by r. And xi plus yj plus zk is the vector r itself. So this is the vector r itself divided by the magnitude of the vector r. So let me write that. And that's what we usually denote by r hat, right? When I wrote r hat here, that's what I meant, right? It's a vector r divided by the magnitude of this. So gradient acting on a spherical, on the surface of a sphere of fixed radius is in the direction of r hat. If I were to visualize this, so you have a sphere, that's the vector r if you want. If you're on the sphere, so that's your r. So pick a point on the surface of a sphere. What's the direction of gradient of r? That's this, right? That's r hat. If you're somewhere here, that's r hat. So pick any point on the sphere, it is normal to that surface. This is not just on a sphere. The idea of a gradient is that pick any surface you want. Gradient will pick the direction perpendicular to the surface. So it's a way of finding the direction perpendicular to the surface. So that's how you want to interpret it. But we could have, just to show you that the right hand side doesn't have to be this long, we could have done it in the right coordinate system, for example, sphere, and that would have been much easier. So let's see this. This is r, this is equal to r hat d by d r plus theta hat. So there is no theta acting in the function. So at this time you wouldn't write x squared plus y squared. So this is in the rectangle, spherical coordinates. So this operates to 0. This operates to 0. So d by dy derivative of r with respect to r is 1. So that's r hat. So another way of evaluating that identity. Again, if you generally, so this is a generalization. So interpretation or geometric interpretation of gradient. Again, there are more than one geometric interpretations. Often this is convenient. Sometimes we also think of it as the largest descent you can have in the particular in a direction. But this comes out to be a lot more useful in gravity and electrostatics. So this will be equal to, so if you have a gradient operation of a function, again think of this as a function of x, y, z. But this is all right. So in general, left hand side you want to write it independent of the basis. Any position dependent quantity, scalar function we are doing at this point, and this is a gradient operator. Again, we want to think of this as basis independent. An example could be the temperature in this room. Right? This function might be describing, give me a point x, y, z. I'll tell you what is the temperature at that particular point. At this corner of the table, it might be let's say 75 degree Fahrenheit. At this corner, it might be 77 degree Fahrenheit, and as you move one point to the other, you're changing the temperature. So how you want to look at it, how does a surface come at all? This is a temperature. I don't think of it as a surface. It is a volume quantity, right? At every point in space, there is a temperature. How do you get a gradient operation from that? Write this as gradient, and f of x, let's say f minus f naught. So what I have done is that this is a constant, so gradient of a constant is 0. So such that where gradient of f naught is equal to 0, right? This is a constant. And what is f naught? Basically, f minus f naught is equal to 0 means f is equal to f naught, and f is equal to f naught are surfaces of equal f. So we talk about equipotential surface in electrostatic, where the voltage is the same or potential energy is the same. You talk about gravitational or a surface on which the gravitational energy is a constant. So this is a surface of constant function f. We talked about the temperature. We will talk about a surface in this room where the temperature is exactly constant, and they will always be one inside the other. If it's a continuous function, we will talk about nice functions which are having nice features to it, and then you can pick any number you want, and you're talking about things being perpendicular to that. So this will be perpendicular to equal f surfaces. So again, example. So let's go to electrostatics. This works for gravity also. Electrostatics and gravitational force are very similar, at least at this level, not in general, but at least at this description, it is very similar. Let's think of electrostatics of a point charge, let's say. This is just an example. Whatever I'm going to write is very generic. What is the electric potential due to a point charge? One point charge at the origin, let's say. What is the electric potential due to that?
Phi equals to minus of phi to.
Now go back, more elementary, no gradient. If you have just one positive charge at the origin, what is the electric potential at a point in space near to it? Yes, say that again?
1 by r.
Yeah, so it is 1 by r, correct? So you have, if you're in SI units, there is a constant, so that's 1 over 4 pi epsilon naught times q over r, right? So this is not important. So this is a unit dependent quantity which units you have. So it's just 1 over r. If you bring in another charge, so this is also in elementary physics, man, most of the literature there's V these days. In the modern literature you have V there, but I'll use phi there. and potential energy is you multiply by another charge, right? So this is 4 pi epsilon naught, and this is usually having two charges. Same R, but now here R is, so this is R is R1 minus R2. So this is the position of charge 1, this is the position of charge 2. Agree? What is R here? This is R1 minus
It's at the origin, just.
it is at the
If it's centered at the origin, then it's.
I said the charge is at the origin, let's say, so R1 is at 0. What is the other distance?
R2.
R2, I don't have a charge there, right? So there are two charges here. There's only one charge here, which I placed at the origin. So R1 is technically 0. What is the other vector? What is the interpretation of the other vector?
They're only the same point. We are doing.
So we are saying, so we are having a positive charge here, right? So let's say this is the origin is somewhere here, so that's R1, right? And we talk about the potential at a point, right? So it's an observation point, so it has nothing to do with the position of anything. It says any coordinate in space. The moment you put a charge, every point in space has an electric potential. So it's a property of the whole space. So that's the difference between this. Here, this is a property of two charges. There's nothing to do with space. That's why this is a field. This is an energy. This is a field in the sense that at every point in space, there is an electric potential. It's a property of space-time in a sense, if you want to say it in that way. So this is R. This is observation point or any. So this is an observation. And that's what we will be interested in. The moment there is an R, we want to take a gradient and a gradient operation on that. So that's phi and u. What is electric field? Due to a point charge. Electric field. Help me.
Q by M square.
Q by R square, that's all?
1 by 4 pi epsilon.
And that's all? Q by R square, that's it? Anything else?
In an R.
Hat, right? Good, that's a vector, right? Is there a connection between the two?
One is minus the derivative of the other.
Very good. So it is an, and if you can take any potential, and this will be always true. I said this is for a point charge, but this is always true. At any point in space, electric field is always equal to the gradient. And notice a gradient operation coming in. So we want to talk about that. This is a field concept. So maybe I should say these are fields, which is more. It has a deeper insight with the idea of field. And here, this is energy and force. You can say this is action at a distance. This is how we studied, we understood electricity and magnetism before Maxwell came in. I shouldn't say Maxwell, before Faraday came in. This is how we understood electricity and magnetism, but now we understand it as a field theory, and it is significantly different. Here, this will be the force on charge 2 or 1, and this will be equal to 1 over 4 pi epsilon naught, Q1, Q2 over R squared, and then there is R12 hat, where R12 will be the direction between 1 and We are interested in this piece here. If I have a point charge, just one point charge, right? I have to draw a surface of equal potential. How will they look like? I have to look for every point in space where the voltage is, let's say, 3 volts. How will it look like?
That'd be like a field line. Field line where it traces out all the places where voltages.
Yeah, so how will it look like for a positive charge? Every point in space here, which is exactly 3 volts.
So it'll be some circle around it. Like
Sphere.
Yeah.
Not a circle, it will be spherical. So you have, so these are equipotential surfaces, you call it?
Yes.
Right. So this is surface of equal phi, equal voltage. If I take the gradient operator for phi, in what direction will it be? Gradient of equal surfaces. Gradient of equal f will be perpendicular to that surface. So it will be perpendicular to that surface, and you have to draw that at every point, but I'll connect them together, so that's your electric field. Okay. There is a negative sign here. What does that negative sign mean? Now I have a choice. Every time there is a perpendicular, I can take it inward or outward. And if this is at, let's say, relative to these 2 points, which one will be higher and which one will be lower in the potential?
Higher potential.
High, low. Which one will be higher, which one will be lower?
Higher potential closer.
Higher towards the positive charge. As you get closer and closer, it's getting more and more positive value. So this is, as you reach a 0, it will all the way go to infinity. So this is high phi. The high values for phi, and these are lower, relatively lower values of phi. Okay, and that's the interpretation of this negative sign. This is also true for the force and energy. Remember, force, the electric field, is negative gradient of phi, and force is negative gradient of potential energy for every conservative force. So this is for conservative forces. Quiz. We are going to talk about electricity and magnetism. Electrostatics is a conservative force, which means the force can be written as a gradient, a negative gradient of a potential energy. So the quiz is magnetic force is magnetic force. What is a magnetic force? What's the expression for the magnetic force? On a charge, on a positive charge? Magnetic force? If there is a positive charge in an electric field, what is the force? Q times E, right? So if you have a positive charge in an electric field, it could be anywhere, like it doesn't have to be uniform, so I have a positive charge here. So the force on that is charge Q times the electric field, right? So that you say that's an electric force. If a charge is in a magnetic field, what is the force? So Q times magnetic field?
V cross B.
V cross B, very good.
Yeah.
Right, so the question is that a conservative force or not? Is magnetic force conservative. So we are talking about gradient operator, and this is the gradient operator, and that's the interpretation. Every time you see a gradient operation, that is the way you want to visualize it. There are other operations that shows up. Since it's a vector, I can take a dot product, that is a divergence, and there is a curl also. We will talk about that as we proceed, but let's try to see operations involving gradient operator, and if we can use index notation to get some identities associated. So recall, let's say, D crossed with A crossed with B. Since you guys have done the homework, what is this equal to on the right hand side? And let's say there is no quantum features here, they are all commutative. A, B, D are commutative, so A, B, E are numerical. Okay. So what is that equal to? Yeah, back cab. So you would say
D dot B.
A times. So you start with these two are the vectors that are free. So that's A times D dotted with B, and minus of B times D dotted with A. They can be written in different ways. So let me write it like that. Okay, is that correct? Okay. Now I want to. So let's do. So example now. So if that is true, what can you talk about the gradient? Gradient is basically a vector A crossed with B. This could be the electric field, that could be the magnetic field. So that's the way you want to think of it. All these are fields in the sense these are position dependent vectors. So at every point in space, you have a value for A, you have a value for B, and you want to do that operation. How will this look like on the right side?
A times divergence of B minus B times divergence of A.
So A times divergence of B minus of B times divergence of A. Is that correct? Is that correct?
B, C, C. Yep.
Usually, a gradient operator doesn't become a vector. So this will be, we will see that this is not correct, okay? This will be partially correct, little bit, but usually it doesn't, because this has to act on things. Like this is an operation, and this is this is just a vector. So it doesn't act on A and B. Right? Here there is an action, so it is not straightforward, so we have to redo that calculation, taking care of the fact that gradient operation is involved. So let's see what happens. Let's call this C. Right? This is again a vector C. So the ith component of C would be equal to epsilon I j k times the gradient, the jth component of the gradient operator, and A cross B. So let me, I can do this for the same step, right? I think you guys are with me on that. I can move this, I can swap this k 2 times, and this becomes, these are all numbers, remember, Levi-Civita symbols are numbers, so this gradient operator acts only on variables. So these are numbers, so it comes out of it. So this is, first of all, I write Kij, Kmn, and the gradient operator has to act on Am and Bn. And I will show that the gradient operator is actually acting on both by putting that parenthesis. Like this means that the gradient operator has to really distribute itself into that. With me there? We have an identity for this. Let me explicitly do that. So this is equal to delta Im delta Jn minus of delta In delta Jm. And gradient operator acting on Am and expand this out. These are Kronecker deltas. Whenever there is a Kronecker delta, when I expand this out, M has to be replaced with I and N has to be replaced with J's. Right? So okay, right, that's taking space here. So this one will become, wherever there is an M, I have to replace with a I. So this is delta J AI times Bj. So notice that I'm doing more than one thing. I'm expanding this out, and then I contracted M with I, N with J. But in the second term, I had to do the opposite. And this is equal to minus of the jth component of the gradient, and M goes with J, and B goes with I. Is that clear? I went here a little faster because I'm assuming that you've done the homework and you got used to that. Okay. So if you're not able to, that means you practice more on the homework. Now we are here. This is where we would have been if we were doing normal vectors like D. But notice now it's a gradient operator, it's a derivative operation. It has to distribute itself. Right? Derivative distributes. So that would be the, so this is your back cab if you want. But now this will split into 4. So open this out. J of AI times J and plus AI times J of set. Actually, that's the first term, and the other two terms are these are numbers, so I can move these quantities wherever I want to. Like A, B, C are numerical, I can move things around. So I move this onto the left just so that I can place them in the right place. So this is B, J, L, J times AI. And keeping a space there just to show that this is J and J is summed here, so that has a meaning, right? This is a dot product. Right. Here, these two are the same, so this is plus AI times LJ. Minus of move I to the left, so you have BI is del u. There is no need for parentheses here. The idea is that the derivatives are acting on the next one. Right? So there are no two pieces there, so I don't have to put in the parentheses. So here I had to put parentheses because I had to clarify that gradient acts on both of them. In general, I won't try to use that explicitly, but in general it's understood that the gradient operator always acts on everything on to the right side. When you're facing the board, it acts on everything on the right side. So if it is not, then you have to close it with appropriate parentheses. And the last one is minus of aj. It is in these kind of operations that the index notation really becomes handy. If it is vectors, it will be harder to see through all this. What is this? These are dot products, and this is your vector. So now I'm really writing it in vector notation. Ith component is the free index. So I is free, and this is dotted. So notice how I'm writing this. This is B dotted with A times the vector A plus vector A dotted with B. Right, that's one of the terms we captured in the beginning. Right, that's the second term here. And next we have minus of B times, and finally that is A with the gradient operator of B. Notice clearly that if we had used gradient to be a simple vector, we wouldn't have captured half of it. Right? Only two things are captured, the other two are not. This clearly brings in two operations of the gradient operator. One is that something could be dotted on the left side, and the other is something could be dotted on the right side, and they have different meanings. So let's try to bring that interpretation out. In your homework, so notice I have used this to be numerical. In your homework, at least there is, I think, in the new homework, not the homework 1, homework 2, there is at least, I think, one example where it is not numerical and the gradient operator is there. So you have to use the fact that you cannot move things around. If you move it, then you have to be careful. So there are two operations. So what's the difference? So there is one is called a directional derivative. Directional derivative, and that is a dotted with the gradient. So this means derivative or change change say f, right? Change in f in the direction of A. Right. So if I am having if I know that the temperature at the corner of this table is exactly 75 degrees Fahrenheit, I can talk about what is the temperature in this direction here, right? One point close to this infinitely tiny point in this direction, or this direction, or the z direction, or in any direction I want to. So this decides in which direction are you doing that derivative. So that's a directional derivative. And the other is a divergence. Divergence is gradient operating on A, and you're taking the scalar product. What is the interpretation of a divergence? Let's say this is equal to the electric field. This is really the electric field now. What is the divergence of an electric field equal to?
Like how it spreads out from a source.
Yes, but what is the right hand side? Very good. What is the right hand side equal to?
Rho over epsilon naught.
Yes, very good, right? So this is equal to rho over epsilon naught. That's a constant, forget that, that's a unit dependent quantity. What is rho? That's a charge density, right? So this is x, y, z, it's a position dependent quantity. So whatever this is on the left hand side, it just checks, is there a charge at that point or not? If there is a charge at that point, charge density, it will give you that value. If there is no charge, it's 0. Right? So usually it is 0. At most of the places, the divergence of E is really equal to 0. Right? If you have a positive charge, for example, 1 charge, what is the value of the electric field here? Like there's 1 positive charge everywhere in this whole universe, that's it. So what is the electric field at this, divergence of electric field at this point?
0.
0, because there is no charge there. Right? You don't have to calculate. If you calculate, it will really come out to be 0. But we want intuition, this is 0, 0. Everywhere it is 0, except where there are charges. Usually we are talking about continuous charge distributions. Even then, in one region there is a charge, and in the other region there is no charge. Wherever there is no charge, it is 0. Wherever there is a charge, it will give you the charge density. It also has this property that wherever there is a charge, the electric field tends to come out. I think Jackson was trying to say that there is a divergence, that's a word of the idea. They will, if there is a negative charge and a positive charge, these charges will try to go out from there and go in. And that can be somewhere here, it can keep going outward like that. So they this cannot be true, right? Quiz. Draw the electric field lines for this path. So let's say plus 5 coulomb, plus 3 coulomb, so minus. Draw field lines. You have to be careful that the field lines never intersect. They always originate from positive charge, and they always end in a negative charge. So why this is not, I was trying to draw a field line like this, but it has to come in. These field lines are going this way and this is coming in. That doesn't happen. Right? So somehow it has to continuously come into this. So most probably there will be a 0 somewhere here. So somewhere here there will be a 0, so that they all come. I don't want to think too much right here. So you have to draw the field lines and you will get a feel for what divergence is at that point. And again, if I were to calculate what is the divergence of E at this point, so that is exactly equal to 0. We can also think of a curl operation. So so if it's just a single point charge that shows up in your homework, but that's in the next homework. Yeah, this is sufficient. Yeah, I think I will stop here. Let me not start a new example. Okay. Again, come and meet me if it is not smooth as to what are the operations going on if you're having difficulties in the homework. Thank you.